Now we discuss the next article, Gauss divergence theorem. In that case, firstly we explain what is the statement of Gauss divergence theorem, and then we prove that how volume integral transform into surface integral. Now firstly we explain what is the statement. The statement of the Gauss divergence theorem we give here. The volume integral of the divergence of a vector point function over a closed volume V is always equal to surface integral of vector A over the closed surface S, which encloses that volume. It means we are considering A is a vector point function. That vector point function, we have to take its volume integral, and how that volume integral changes to surface integral. That part we discuss one by one. Mathematically, the statement of Gauss divergence theorem is represented as the volume integral of divergence of the vector point function A over the volume V is equal to surface integral of the vector point function over the closed surface S. That surface encloses the volume V. Or this equation is also written as divergence A or del dot A dV, volume integral of del dot vector A dV is equal to surface integral vector A dot unit vector n ds. Now what is vector ds? That vector ds is represented as unit vector n ds. That unit vector n unit vector is a unit normal vector drawn outward at each small surface element. That part we explain in the next point. Now how the unit normal which drawn outward at each small surface element. Now we have to prove this statement. For that we are considering a closed surface. Yes, that surface which encloses the volume V. V is the total volume. In that volume we consider small element. That small element volume we express in terms of Cartesian coordinate system. And if A is a vector point function at a point in that small volume element, that vector point function is also has three components along x, y, z axis. Therefore, that vector A, which defined as unit vector I ax plus unit vector j ay plus unit vector k az and small volume element dv is equal to dx dy dz. Means vector A is known, dv is known. Then we simplify the one side of the equation 1. That means we find the integral volume integral of del dot A dv or divergence of vector A dv. Now what is del term? That we know, we discussed earlier. Volume integral V into bracket. We write firstly del term. That del operator is defined as unit vector I dab of dab x plus unit vector j dab of dab y plus unit vector k dab of dab z. And the vector A, that vector point function in terms of its component ax, ay, az defined as unit vector I ax plus unit vector j ay plus unit vector k az into dv. dv is the volume element in Cartesian coordinate system. That volume element is dx, dy, dz. Now we simplify these two bracketed term and we write volume integral V del dot A dV is equal to. Now if we take the dot product, vector unit vector I dot I is 1. Unit vector j dot j is 1. Unit vector k dot k is 1. But unit vector I dot j is 0. Unit vector I dot k is 0. In that way, two different unit vector and their dot product is 0. Hence, we get only the simplified term. Volume integral dabba of dabba ax by dabba x, since unit vector I dot I is 1, plus unit vector j dot j is 1, therefore dabba ay by dabba y, plus unit vector k dot k is 1, therefore third term we write plus dabba az by dabba z. Outside bracket we write dx dy dz. Now we write the three terms separately. First term multiplied by dx dy dz, second term multiplied by dx dy dz, third term multiplied by dx dy dz, and their volume in terms of volume integral we write the simplified term volume integral v dabba ax by dabba x dx dy dz plus volume integral v dabba ay by dabba y dx dy dz plus volume integral v dabba az by dabba z dx dy dz. Say this is the equation number 3. Now, in that equation 3, we solve the first term. If we solve the first term, we write similarly what is the value of second term as well as third term. Now, for that one, we write the first term as it is. The volume integral dabba ax by dabba x dx dy dz is equal to, this integral we simplify by taking the integral of only dabba ax by dabba x dx. Other term we kept as it is. Hence, integral of dabba ax by dabba x dx, that term we only simplify here into dy dz. For that, we considering a small portion of the surface which is along the x-axis. That small surface we draw at the 2 points which are at ds1 at the point p1 and ds2 at the point p2. Now, how we represent the small portion of the surface element along the x-axis, that we draw here. Now, this is the whole closed surface and inside that one which encloses the volume V. In that volume V, we considering a small volume element. That volume element, we know that it is dx dy dz. Now we suppose here inside the volume we consider the very small portion of the surface element which lies along the x-axis. Therefore, at the point P1 the surface is ds1 and at the point P2 we write the surface ds2. At the point P1 the unit normal is directed outward to the point P1 and at the surface ds2 the unit normal drawn outward to the point P2. Hence, we find the first term. Now, we discussed earlier. Now, we have to simplify only the integral of dabba ax by dabba x dx. Now, what is the integration of dabba ax by dabba x dx? This is ax. Means it is the rate of change of the vector point function along x-axis with respect to x. That is ax. That ax which is varied in between the point P1 and P2. Hence, the limits we take the integration P1 to P2 dy dz. Now, if we take the upper limit P2, lower limit P1, then we simplify the term ax at P2 minus ax at P1 dy dz. Now, what is the term representing here? we write the two separate terms separately right here. Surface integral ax p2 at p2 dy dz minus surface integral ax p1 at p1 dy dz. Now what is ax p2? Ax is the at the surface p1, the direction of x component of the vector A, which is opposite to the direction of the outward normal to the point P1, and therefore the flux at point P1 is negative. Hence, the integration, if we that first integral term, in that case Ax at P1 dy dz, it represent the negative flux at the point P1. Since the x component of the vector A is opposite to the direction of the outward normal to the point P1, and therefore the flux is negative at the point P1. Hence, that value we write firstly. Ax at P1 dy dz. Dy dz is the surface area of that small element, that we call the ds1, same as the surface area at the point P2 is same, that point we call ds2. Hence ax at P1 dy dz is equal to minus ax dx1, and ax P2, what it represent? At the point P2 or at the surface P2, we get the direction of the x component of vector A is in the same direction of the outward normal to P2. In that case, the flux is positive. Here, flux is negative. Hence, instead of ax p2 dy dz, that value we directly write ax ds2, and surface integral ax p1 dy dz, that value we write minus ax ds1. Since the unit normal which is directed outward at each small element, that is small element is at the point P1, P2, ds1, ds2. Therefore, the equation 4 becomes, what is other side of the equation? Other side, surface into volume integral dA by ax by dA by x dx dy dz is equal to surface integral ax p2 dy dz minus surface integral ax p1 dy dz. Therefore, we substitute these two terms in that equation and we write the equation 4. We rewrite volume integral dA by ax by dA by x dx dy dz is equal to surface integral ax ds2, since flux is positive, minus surface integral minus ax ds1. This minus ax dx1, it represent the flux is negative at the point P1. Minus minus it become plus, and we get surface integral ax ds2 plus surface integral ax ds1. Now what are ds1, ds2? These are the small surface element of the small portion of the surface which is taken along x-axis, and therefore the surface integral ds1 plus ds2, this is nothing but the small surface element along the x-axis, that is surface integral dsx. Hence, the above equation we again write in the simplest form. Volume integral dA by ax by dA by x dx dy dz is equal to surface integral Ax dsx. Similarly, we find the another term in the equation number 3. What is another term? Volume integral dA by Ay by dA by y dx dy dz is equal to, directly we write the equation, next equation number, surface integral Ay dsy. Since this is the another small portion of the surface which is taken along the y-axis, and that component we write directly surface integral Ay dsy. Similarly, another same small portion of the surface which is taken along z-axis, that is volume integral dA by Az by dA by z dx dy dz is equal to surface integral Az dsz. Hence we get the three terms in this equation number 3. Hence we write, simplify the equation 3 by putting the values of 5, 6 and 7. The equation we again simplified. The volume integral divergence of the vector point function over the volume dV is equal to surface integral Ax dsx. That value is for which one? Volume integral dA by Ax by dA by x dx dy dz. Similarly, the second term is the result of volume integral dA by Ay by dA by y dx dy dz. That is the equation 6. And what is the third term? Equation 7. Since volume integral dA by Az by dA by z dx dy dz is equal to, that term is known. Hence we put directly Az dsz. Now we have to simplify this term. Taking common term integral surface integral, and we write inside the bracket Ax dsx plus Ay dsy plus Az dsz. Now how we get that term? If we take the vector point function A dot small surface element ds, vector ds, hence what is vector ds? This is unit vector I dsx plus unit vector j dsy plus unit vector k dsz. Hence, this equation is we write in the form of vector A dot vector ds. Vector ds is again we write in terms of surface integral vector A dot unit normal drawn outward at each surface element ds. Hence, nds is vector ds. Hence, the equation we get volume integral del dot A dV is equal to surface integral vector A dot unit vector n ds or surface integral A dot ds. This equation A represents Gauss divergence theorem, and it proves how the volume integral transform into surface integral. Now then we see what is its physical significance. For the physical significance, we explain by using the equation A. Since equation A is the Gauss divergence theorem, in that equation, what vector A represent? A is a velocity vector. That velocity of incompressible fluid we just take into consideration. Means if we consider the incompressible fluid, its density is 1. Hence vector A represent, it is the velocity of incompressible fluid whose density is 1. And what the divergence of the vector point function represent? Divergence of the vector A, it represent volume rate at which the fluid is flowing, and that volume rate gives the intensity of the source. Hence divergence of the vector point function, we write it is a source. That source which changes its volume rate at which the fluid is flowing. Hence integral term of surface integral vector A dot unit vector n ds. It represents amount of fluid flowing per second across the surface. Yes. And volume integral of divergence of the vector point function A over the volume dV. It represents volume of fluid supplied per second by the source. Hence, we say under that physical significance, the vector point function is a vector which represents the velocity of incompressible fluid. And that fluid, how much fluid is flowing per second across the surface, yes, it transforms into the total volume of the fluid supplied per second by the source, and that gives its physical significance. Thus, in this today's lecture, we discuss firstly what is the statement of the Gauss Divergence theorem, and we know that theorem which is related to how the volume integral transform to surface integral. Hence, the statement we again explaining here, the volume integral of the divergence of the vector point function over the closed volume V is always equal to surface integral of vector point function over the closed surface which encloses that volume. And that statement we prove here, and we get the volume integral transformed into surface integral. Thank you.